There are three little words that I seldom say to my tens of subscribers. You guys suck. No sooner than I release a video about how I recreated the wheel in combining stars with a starless image, than you reply back with an even better method that already existed and points out the flaws in my method. Of course, I'm just kidding. And so I want to take a look at that method and compare it to my original pixel replacement method, and then finally show some improvements that we can make with the blending method to better enhance the star color that we get in our final image. Let's get started. This is the pixel replacement method script in the last video in PixelMath, and what you see here is basically just the process of getting the color in the nebula, the color in the star, and whenever the star color exceeds the color in the nebula at that same pixel, then I just copy the star pixels from the star image over to the starless image, and that's how I preserve the color and also avoid saturating the stars. Then a lot of the commenters pointed out the combine method that can be implemented in PixInsight, where you use the combine generator along with the two images. The $T here, that's the target image, that's the starless image. The stars image is the image such as this shown over here that's just been renamed to stars. And then finally this function that provides the blending operation. Now that function is actually very simple, and I could take this RGBK expression. Notice that here there's only one RGBK expression, whereas over here you're copying these lines into the green and the blue as well, and then making a change to this final line. But over here it's just one expression, and I can rewrite this line to be a simple function like this, where I have, again, the starless image is $T, the stars only image is stars, and then it just calculates 1 minus, and then the product of 1 minus the starless image and 1 minus the stars image, and that would give us the same effect as this function here. So that expression in PixInsight is totally equivalent to this expression. Let's take one more step and re-express this equation into an even simpler form. Here we have the starless image plus the stars image, and so in our last video we talked about what happens if you just add the stars to the starless image. That's when you get the saturation and the bloating and you lose all your star color. So that right there is the essence of the adding the stars to the starless image. What this blending method brings in PixInsight is this extra term here where we subtract off the product of the starless image and the stars image. So for example, let's say we had a pixel that had a brightness of 0.5 in the starless image, and we're going to combine that with a pixel in the stars only image that is also at 0.5. We would have something like this, which would be right at the saturation point. But then this formula here has this part we subtract off, which is 0.5 times 0.5, which is 0.25. And so we would subtract off the 0.25 and get 0.75, which is less than 1. So we're not saturated. So this brilliant little expression is preventing us from getting saturated. Let's try one more example where the starless image has a brightness of 0.4 and the star pixel is pretty bright at 0.8. If we just added these two together, then we're going to get a 1.2, which of course is saturated. But with this method, we will be subtracting off the product of 0.4 and 0.8, which is 0.32, and we come out to 0.88, which is less than 1 and still not saturated. So the math here in this blending function is actually quite brilliant, and it prevents us from saturating, and therefore it prevents us from getting bloated stars. Another big advantage of this approach is that it provides a nice blending around the dark boundary of a star into the nebulosity, so it doesn't look the abrupt application of star color, which is what results from my method over here. So what are the pros and cons of the replacement method versus the blending method? Let's go over to PixInsight and take a look at these two. This same example I was using in the previous video, I've got SH286 over here. This is my starless image. And this is the stars only image where I collected RGB data for about 30 to 40 minutes on each color and then combined them and used photometric color calibration to calibrate the star colors and then use StarNet to pull out those stars. And I've zoomed into a section here that we'll go back to and compare because I've got some stars here with some decent color, some red stars, maybe some small yellow stars here, maybe larger blue stars up here, and some very faint stars that are also in this image. So we'll take a look at this field of view, highly zoomed in obviously, to see how these two methods work with this data. Now the first thing I'm going to do is look at the blue field here, representing a constant level of nebulosity and a constant color, so that we can have a better idea of any artifacts associated with these two methods. Now the first thing I'm going to do is apply the replace stars algorithm. That's the one that I talked about and introduced in the last video. If the brightness of the star pixel is greater than the brightest of the color pixels in the nebula image, then we just do a simple replacement where we just map the stars over here in this image over into the location over here in this quote nebula unquote image. And so I can just run this by dragging this triangle over into the field and let it do its thing. And we get this resulting star image. Now, one of the things about this image, and we'll see this when we compare it to the blending method, is it will appear like we've lost quite a few stars. And this is particularly true when we apply this method to the brighter nebulosity image of SH286. But for now, we'll focus on this particular image. And now let's zoom in to this area of the star field so that we can see how we handled these different stars here. Now, there's a couple of things that jump out at you. First of all, the stars jump out at you because there is no blending around the boundary here. The stars look like they're basically pasted on, which is not a terribly realistic effect. To be fair, we are way, 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 way too far zoomed in on this image. Nobody should be looking at their images at this level of detail. And I would prefer some blending to go on around these stars. Now, on the positive side, I am retaining every bit of star color that I have over here in this star image because, after all, I'm just copying the star pixels from here into the nebula image and replacing the blue pixels that were already here. So as a result, I retain 100% of the star color. Now, again, on the negative side of this image over here, you'll see some of these stars here, these fainter stars that are over here that I can see. You may not be able to, but their brightness does not exceed the brightness of this background blue color, and as a result, they don't show up at all. It does provide a nice effect to have fainter stars present along with the brighter stars. This is the star replacement method, and you can see it does have some advantages, i.e. it brings the color in. There's no additional saturation, there's no bloating, but it has some disadvantages. There's no blending in around the star boundary, and I'm losing the fainter stars. Now let's take a look at the blending method. So here we have that function. We have the starless image, which is our target image. We have the stars only image, which is this image over here. It's named stars right here. It also has the additional feature of the blending method, which is to subtract off the product of the starless and the stars only images. And so now we can simply apply that in the same way. And now you can see what I'm talking about. You get a sense of a lot more stars in this field than we had with the replacement method. For example, let me bring that up and go to full view and set them side by side, and you can see that there appear to be quite a few more stars over here in the blended image than there are with the star replacement image. But now let's zoom in on this area of the star field where we have some colored stars. One of the nice features is we're retaining these faint stars. They are still being added in. We're getting some very nice blending from the constant blue background into the star. But one of the things that you quickly notice is that our star color is not the same. We are losing quite a bit of our star color because we're blending this reddish star with a bluish background, and as a result we get just a hint of the original star color that we had in our star images. Now we can contrast that with the star replacement method at the same field of view, and you can see that we have much more color over here, but there are some consequences to using the star replacement method in that we don't have the blending and we lose the fainter stars. Both methods are successful in that they don't saturate or don't generate any additional saturation when we combine the stars to the starless image. We don't get the resulting bloating that comes with saturating the pixels around the stars. The pixel replacement method actually does a better job of retaining all the star color. The blending method, which has some nice effects, one of its downsides, and perhaps its only downside, is that you're also blending the color of the stars with the colors of the nebula behind it, and as a result, you're losing some of that star color. One of the big disadvantages of the pixel replacement method is that you can clearly see the abrupt edges of stars, which is not very satisfying. It's kind of unrealistic looking. The blending method is awesome. It does a great job of taking the faint edges of stars and blending it in with the nebulosity. It leaves you with more natural looking stars in the foreground and nebulosity in the background. additional problem with the pixel replacement method is that I'm losing the dimmer stars. They're no longer visible. The blending method actually does retain all of the stars, even faint stars, and that creates a more realistic star field. StarNet will sometimes leave artifacts in your starless image after it pulls out the stars. A nice side feature of the blending method is some of those artifacts are kind of averaged over in the blending process and you don't see those artifacts. Is there some way of putting these two methods together so that I can get all green? I can get all of my star color, or at least most of my star color, and all of the benefits of the blending process. So let's talk about the color enhanced star blending method. Essentially, this is the same PixelMath expression that I had for my pixel replacement method, but I've replaced the pixel replacement parts. So we're going to have entries in the red, the green, and the blue tabs. We're going to operate with this the same way, so we're going to do a drag and drop of this triangle onto the starless image. And the first bit of code here is also the same. I pull out the red, the green, and the blue pixels of the nebula image, find out which of those is the maximum. I do the same thing for the stars only image, find out which is the maximum color brightness, and then here's the departure from the replacement method. I'm now incorporating that formula that we saw for the blending. So this is kind of a blending factor that I'm going to make use of. First of all, it's going to prevent the saturation. It's going to provide blending around the faint boundary of a star and the nebulosity behind it. And third, it's going to allow the fainter stars to survive the merging with the starless image. Now, the one departure that I'm doing from the blending operation is this line right here. And it looks a little complicated on the surface, but let me just give you an idea of what it's doing. This function here, this 1 minus cosine function, is a curve that looks like this. It's low when the star brightness is low, and then it rises up to a value of 1 when the star brightness gets up to its maximum value of 1. And what this is doing is when the star color is low, that is the area around the very periphery of a star or between stars, this expression here goes to 0, and all you're left with is the color of the nebulosity, which is what you want. When there are no stars, when it's a black background in the star field, you don't want any star color coming through into that pixel, and it doesn't here. Now, as you start ramping up and the star color starts getting more and more prominent, now what's happening is we're getting this blending of the star color with the nebula color in those pixels, and now we're seeing a more smooth blending of colors. However, what's happening here, and the difference between the blending method and this color enhanced blending method, is that this curve rises much more rapidly, and as we move up into this part of the curve where the star color is really getting more bright, more obvious, then in effect what this function is doing, it's converting the nebula colors, the RGB colors in the nebula, to have the same color balance as that pixel does with the RGB colors in the star. So in effect, I'm blending an RGB set of colors in the star with the same color balance of the RGB colors in the nebula. The nebula and the star have the same color balance as we move higher up on this curve, and therefore blending one color balance with the same color balance of the nebula produces a star color that's a lot closer to the original star color in our star image. As before, you'll just copy all of these lines into the green tab and the blue tab, and down here in the last line you'll change the R to a G if it's in the green tab, change the R to a B if it's in the blue tab. Let's take a look at that in PixInsight and see what we have. Here's the color-enhanced blending method script in PixelMath, but let's create this PixelMath process from scratch. I'm going to go ahead and reset this, and then for you will go over to the description of this video and copy in the lines. For me, I've got those lines for the red channel over here in a text file. But first, let's check this box here to convert over from a single RGBK image to a full RGB image in which we have access to the green and the red tabs. We will also change the destination to a new image and make it a RGB color image so that we don't have to create a clone and it will create a new image after the blending operation. So now I'm going to go back to the text editor. For you go to the description of the video. I'm going to select all the lines and copy them, and then I'm going to paste them into each one of the tabs we have here. And I'm going to paste them into the green tab. I'm going to paste it into the blue tab, And I'm actually also going to paste it into the Symbols tab. So let's go back to the green tab. And what I want to do is wherever we have an R in this last line, just the last line, I'm going to change that to a G. And then I'm going to go over to the blue tab and do the same thing, except this time, wherever there's an R, I'm changing it to a B. And then in the symbols area, I'm going to lop off everything after the variable name, but just before the semicolon, I want to keep that semicolon, otherwise you'll get an error. So I'm going to do this for each one of the lines. Now for the last line, we're just going to delete that altogether because we already have an L variable defined, and that should be all we need as far as the symbols are concerned. So now let's save this PixelMath program off as an icon, and I'll leave it there and change the icon identifier to new blend. And I'm also going to save this as a file, an XPSM file, so that I can copy and paste this into future PixInsight sessions. So I'm going to go and do the save selected icons, save it into a common area. You might have several of these PixelMath expressions that you save off for future use, and I'm going to call this new blend here as well. I think I already have one saved, so it'll probably beep at me. It's okay, accept it, and now we've saved that off, and the next time we start a new PixInsight processing session, we can just go and copy and paste or drag and drop that XPSM file into our desktop, and then we're ready to use it in that project. So now using this new blending method, I'm going to move this off over here. So I'm going to blend these stars from SH286 into my blue background field over here so that we can compare with what we did last time with the traditional blending method. And so here's the final result with the stars with the color enhanced blending method. I'm going to call this new, and let's compare this same field with the results we got with the traditional blending method. Just looking at this, I can see a lot more stars than I was seeing with my replacement method. Let's zoom in on the field of view where we have these particular color stars, and I'll also copy that field of view onto the traditional blended image. Now we have a good comparison of the two blending methods. With the color enhanced blending method, you can see that I'm getting the blending that we had with the traditional method. I'm also getting with this new color enhanced blending method, so that makes for a nice transition from the nebulosity into the star. I'm also picking up these fainter stars that were being lost with the pixel replacement method. I'm now retaining now that I'm using the blending technique. The main thing that jumps out at you, and the whole objective for creating the color enhanced blending method, is to try to preserve more of that star color. We've got a good bit of star color down here in these two stars. For example, we've got some yellow stars here, maybe some bluish stars here, and I want to keep that color. But when I use the traditional blending method, that color gets washed out because I'm blending the star color with, in this case, a blue background, and as a result, I'm losing much of that color balance that I had in the star. The whole purpose of the color enhanced blending method is to try to preserve that color in the star so that I'm not losing it after going to all the trouble to capture RGB data. And you can see here we have much more color in these stars than we get out of the traditional blending method. Now let's apply the technique to the actual nebula and see what we get. I'm going to start off with the color enhanced blending method and just drag and drop the icon over onto the starless SH286 image. And here's our blended image. We also have the same image that we got from the traditional blend, and here you see that image. The two were very similar, at least when looking at the overall field of view of the nebula. We're not losing the fainter stars in the nebula, in the brighter nebulosity that we are with the replacement method that I talked about in the last video. Instead, we're retaining that. Let's zoom into one-to-one pixel mode and see what we have. And I'm going to scroll over a little bit to reveal this high density star area that was somewhat problematic when we were saturating those stars. Now you can see that we have a pretty good representation of the stars. They're not bloated, they're not saturated, and I'm getting some good nebulosity in and around this high density star region in both cases, maybe a little more over here. And now let's zoom into that field where we have these stars back in the background. I'm going to drag and drop that over onto the nebula image, and then we'll drop that over onto the traditionally blended image. And now you can see that that red color we had on those stars is retained to a greater degree with this color enhanced blending method than it is over here with this traditional blending method. We are capturing and retaining some of that blue color that's in these brighter, bigger stars here, and we are over here retaining some of the yellow color in these stars that we've lost in these stars over here. So I think the color enhanced blending method is accomplishing our objective of avoiding saturation, avoiding bloating, and retaining some of the star color that we had in our RGB star image. So the main problems I wanted to avoid when adding stars to a starless image was to avoid the saturation and the resulting bloating around those stars that results when you add a bright star to a bright nebula region, and also losing RGB star color in those stars that weren't saturated. In the last video, I demonstrated a method that replaces the pixels in the starless image with the star pixels wherever the star pixels are brighter than those pixels in the starless image, and that worked very well in that it didn't result in any saturation, it didn't produce bloating, and it recovered 100% of the RGB star color and put that into the starless nebula image. The problem with that approach is that it doesn't really look natural because you don't get a natural blend between the nebula and the faint boundary of the star, and also you end up losing fainter stars because their brightness is not as bright as the nebula that you're adding the image to. And you guys saw the video and pointed out a blending method that a lot of you are using. It's a very clever formula that prevents saturation and prevents bloating and provides a very nice transition from the edge of the star into the nebulosity around it. The one problem this method has is because it's a blending method, it's trying to blend the color of the star with the color of the nebula, and as a result, you end up losing the color balance in your RGB star. You tend to gravitate more to a washed out color for all the stars. And that's what led me to create this color enhanced blending method, where I try to keep some of the best features of the blending method, but I wanted to retain all of the star color. Once you set up the PixelMath expression and save it off as a macro, you can incorporate it into any future PixInsight processing session. You drag and drop the new instance icon over onto the starless image, and then that will blend the image whose name is stars into that image using this color enhanced blending method. This color enhanced blending method seems to be working pretty well. If you guys have some time, give this thing a chance. Hey, and thanks for all your input and pointing me on the right path and showing me this blending method. It really is a game changer in terms of blending stars into the nebulosity. Okay guys, well that's all I have for now. Clear skies, and I'll talk to you later. Keep on watching and keep on commenting.